Greetings, everybody. This is the Aftershow for Standing for Truth show with the two PhDs, Rob Carter and Ryan Hayes. I'm just doing some setup here. I'm going to try to put the I'm looking at my other monitor here as I set this up. If no one joins, I'm going to do a monologue. So let me see. I don't know how to make this sticky. Let's see if I can. I'm going to pin the message. And so, okay, Otangelo's here. Greetings, Otangelo. Otangelo, can you hear me? Microphone check. Can anyone hear me? Can anyone hear me? I'm gonna go set something up. Okay, thank you, stuff I watch sometimes, that you can hear me. Thank you all for joining me. I believe Otangelo is still trying to connect. I have the StreamYard link if anyone wants to join the panel. It actually would be appreciated because it's very hard for me to run live streams. As you know, my mother's very sick and I could be interrupted at any time. So I'm counting on you guys to perhaps help me out. So every now and then as much as I say I'm not going to do live shows, it's hard not to participate. And this was such a good show. And then also follow James Tour's show yesterday was just incredible. And oh my goodness, we have a former radio show host in John Maddox joining us. I'm glad to see that you're okay, John. I know that you were apparently in an ice storm down there in Nashville and you're stuck in the ice. We certainly missed your show. Yeah, but thank you for joining.
I appreciate it, man. Yeah, it was quite the adventure. I spent 12 hours in my car last night. At the peak of a hill, another car had slid into me, and it was quite the adventure. But I've made it home again, and yeah, it'd be an interesting story for the memoirs when that day comes.
Any damage to your car?
Not too bad. It's just a little minor dent in the front bumper.
Well, I'm glad you're okay because back in my casino days, I'd be driving there on I-40, and there's one time I saw all these cars just strewn all over the place in emergency vehicles. And like, what's going on? I realized, oh my goodness, it's black ice. And I just slowly.
Oh yeah, I mean, on my way back, it always cracks me up how Tennesseans have no idea how to drive in ice and snow. It's like they go into full scale panic mode and just drive like idiots. So I was about where I got stuck was about 2 miles from Main Road, and anyway. From when I finally got myself up the hill and like off the main road, I counted. So from the 2 miles, I had to go from where I got stuck to the main road. There were 11 vehicles that had gone completely off the road, and some in pretty amazing style too. Like, and some of them were trucks. I'm just like, how dumb do you have to be, honestly, to have done this? I mean, I get sometimes there's things you just can't control, but I mean, part of the reason I got stuck was I was being careful. Like, I think if I had not been being as careful as I was going up this hill, I probably could have made it to the peak. But I got to that point where I just did not have enough velocity to make it up the rest of the way. And then I was just toast at that point. I finally just gave up. But I mean,
I'm glad you're okay, man. 12 hours in your car. 12 hours.
Wow.
The craziest part, though, was not the craziest part, but one of the funny parts was I got out of my car and I literally slid I kept my balance, but I literally slid down the hill probably 30 feet and I couldn't stop myself. It was like I was on a ice rink, just the way that everything had frozen over. But anyway, enough of my tangent.
So I don't know how many of you saw James Tour's talk yesterday, but there was that great graph he showed of the Dunning-Kruger curve, and he said, Professor Dave's right here at the peak of Mount Stupid. That wasn't his exact words, but I was just like, yeah. He said, some people they have so little knowledge and they think they know it all. And Professor Dave is right there in the peak of stupidity. And I was just like, yeah. So that was the best part. I did have some concerns that he took on the thermodynamic argument way too early. Some of you know that I argue the origin of life. I just like, guys, you can use thermodynamics, but you have to really know your stuff. And I don't even classify myself there in terms of understanding thermodynamics. I know it enough to say, don't go there. Don't go there.
Well, so let me ask you, Sal. Thermodynamics has to do with generating proton gradients, which are required. I think we had that conversation with James Carter at my channel, and I think I mentioned this topic, and he said a little bit something about it. And I asked him about ATP synthase, if that would be actually life essential. Remember, he said, well, the thing is that glycolysis also produces ATP, but far not enough in order to drive the energy consummation of even the simplest cell.
No, we were talking about the second law of thermodynamics, not just production of energy. Oh. So a lot of creationists and Brian Miller has weighed into this, and I sent him in emails, and then maybe even publicly I said, I'm kind of concerned about this because I specifically took statistical mechanics and thermodynamics in graduate school to explore this, and I said creationists shouldn't touch this with a 10-foot pole.
Well, since you are mentioning our second law,
so that was the only part. That was the. Oh, I'm sorry. I just briefly. I was just saying that was the only part in Tour's discussion that I just got a little uncomfortable of that he took on.
So can you resume, seeing in a few words what actually the argument is? Because you just took me by surprise now that the thing that they are arguing about is the second law of thermodynamics. Can you?
Yeah, this all began with Duane Gish, and he was saying the second law of thermodynamics prevents abiogenesis. And it's like there are a lot of things that prevent abiogenesis, but the second law of thermodynamics, trying to apply it is like trying to use a sledgehammer to kill a mosquito, especially if the mosquito is resting on your head. It's just.
But this is a very old argument, which we heard a decade or so. It was very often used. And the common reply by atheists was that, well, that the Earth is not a closed thermodynamic system, but constantly receives energy from the sun. Okay, so I'm not saying abiogenesis is right. I'm saying which arguments we should use. And so my point is right there in James Tour's video, he said, Brian Miller was talking about we have to lower entropy. I'm just like, that's such a vague assertion if you're not talking about the thermodynamic boundaries. I mean, there's a lot of things you have to do to qualify what you're saying, and that's why I don't like it. Well, I would
so, for
say
example, I'll give a specific example. Go ahead, Angelo.
Well, I think the big issue here is really how do you get the disequilibrium at the beginning in order to drive life? Because if we are at equilibrium, then we have no life anymore. Then the cell is dead. Yeah. And we require to actually generate that disequilibrium, and that requires the proton gradient, which actually is necessary in order to have...
That's not the only disequilibrium condition, but I'm going to give something even more basic because I'm concerned there are science students that are juniors and sophomores in college. They will learn things like standard molar entropy. I will ask them, and I confronted Dr. Miller, who was on James Tour's show last night. I said, I feel uncomfortable with this because if you keep saying you need to lower entropy with life, Here's a counterexample. What has more entropy, a warm living human or a frozen dead rat? Which has more entropy? Any chemistry student at the sophomore level, an engineering student who's studying thermodynamics, any of those, or a physics student, any of those who understand the concept of standard molar entropy should correctly say a warm living human has far more entropy than a frozen dead rat. And so I have a lot of issues with saying, oh, to make life you have to lower entropy. It's kind of a yes and no because it depends on what parameters you're talking about. And it ends up being so vague. It's like, well, why even invoke the second law of thermodynamics? You can make a far clearer argument without invoking the second law. So I was just like, okay, this is really bad because just to open up an argument like that, and the first thing someone will ask, show the delta S between, delta S being the symbol for entropy, show the delta S between the living state and the dead state. If you take a human being and you kill him by freezing him to death, you've lowered his entropy. So the delta S is lower. It's not good to be saying you need to lower the entropy. It's problematic. The other thing is Brian Miller equates entropy with disorder. That's kind of an obsolete view. Unfortunately, it was started because of passing remarks by Boltzmann and Gibbs. And
well, there is another ingredient, which is the information in the cell, which has nothing to do with entropy.
Well,
it has to do with information entropy. But what we are talking about, that in order to have a high ordered state, which is required, and the high complexity in the cell, you require specified assembly information, and that has nothing to do with entropy.
So my point was that was the only part I had issues with in the show. And James Tour said just watch the Brian Miller video, which I was kind of glad of, because I know the rest of the stuff he's going to argue is going to be very solid in terms of pure chemistry.
Yeah, he is very.
In terms of arguing, I know the 13-part series, he's just going to crush Professor Dave.
Oh,
and every slide was wrong, which I was laughing at.
Yeah.
Because even I could see it. And for those, I hope some of you have seen my video on correcting Professor Dave's cow pies. Now, cow pie is a polite word for what we would call coming out of the excrement coming out of a
bovine scatology is the politically correct way to say it. Bovine scatology.
Yeah,
no, Brian,
I came up with cow pies. That's because we try to keep a family-friendly channel here, and I'm not kidding. A woman from church was directing 13-year-old girls to my channel. I'm just like, oh my goodness, one, this is a highly technical channel if you've not noticed. But then I'm just like, yeah, we have to kind of keep the language we have to try to keep the topics and the behavior as family friendly as possible. Just a heads up, everyone, so.
Yes, but the energy issue, which is one of the, I would say, the three fundamental requirements for life, that is, of course, a big issue in regards of abiogenesis and the origin of life. I mean, how do you get ATP prebiotically? We know that to make ATP, it is very complex. And not only the last step to add the third phosphate through ATP synthase, but to make ADP as well. It is very complex, and the cell requires many enzymatic steps to make it. And these steps were obviously not extant prebiotically, and the cell uses a huge amount and has to produce this continuously. So how do you get there? That's a huge problem.
Well, that's all that I had to say about James Tours. I mean, it did bother me all day. Oh, maybe I could share this. And this was one of the best parts of James Tours' talk yesterday. See if I could. Oh my goodness, this was savage. Let me share this. So James Tour yesterday, he was trying to describe Professor Dave, And he said there are these people who know nothing, and then some of these people that know something, and they just think they have very high confidence in their knowledge. And then once they start to learn something, they go into this valley of despair. And then they, if their position is correct, and in the case of Professor Dave, it's not, they start to have a little more confidence. They have the plateau sustainability. And he specifically said, this is where Professor Dave is here, the peak of Mount Stupid. He knows nothing, close to nothing. He's a pretend professor. And as Logical, Plausible, Probable pointed out, James Tour is like one of the top 50 chemists on the planet. He has the authority to look at Professor Dave and say, you know nothing. You're at the peak. You're full of confidence and you know nothing. That puts you at the peak of Mount Stupid. That was the highlight of the show.
Now, it was funny, Sal, that yesterday I like to go in these call-in show streams and just to put my messages, which I copy-paste. And I had a call-in just once at the line with Jimmy Snow about 5 months ago or so. And I brought up the improbability to have a first proteome, to have the kickstarting of life. And then he made a refutation video and called me dishonest, but he didn't refute anything of what I said. So yesterday I put a quick message regards of that and said, hey, you called me dishonest, but you have still to back up what you said. And then he saw it and he recognized me, and then he put exactly that graphic, and then he said, oh, it's Untangelo, that he is Dunning-Kruger. And they were just laughing at me and so forth. And then after the show, I did post at his timeline and said, well, if you are calling me Dunning-Kruger and name calling me, that shows that you have actually no argument to refute what I said. And then he repeated again, you are a Dunning-Kruger. And then I said, well, so let's do this. Either you can refute what I said, and then I copy-pasted my argument. And if you cannot refute it, then whatever you said against me fires right back against you again. And then I put the calculations in regards of having a first proteome and the odds. And of course, he couldn't answer. And I am still waiting for him to reply and actually refuting this argument.
And who is this gentleman?
His name is Jimmy Snow. He has a huge audience. I think he has over 300,000 subscribers.
Wow.
Yeah, his show is he's pretty popular. He's a clown show though. It's he has no idea what he's talking about.
No, he doesn't.
A good portion of this stuff. I'd say sidebar, Otangelo. I mean, you probably know this because of I know you're very fascinated by the ribosome. I was watching a lecture, actually 2 different lectures.
Yeah, you did send it to me. I started to watch it, and I will end to watch it because it started pretty interesting, and I'll still look it all. So one of
the things they discussed. We're going with this. You may have probably read a paper on this at some point. Sal, you may have as well. The dual ratchet effect in the ribosome from actually moving the mRNA along is fascinating. Have you read up on that, Sal? And
No.
Okay, so it's a literal motion, controlled motion. There's hinges, and it actually. Long story short, there's like 2 different motions that are happening between the main unit and the subunits, the different subunits, right? And in a literal ratchet motion, okay, it pulls the mRNA along for each codon. Like we know that it goes codon by codon. We already knew that portion of it, right? But like the actual how it's happening, how it's being executed, it's some mind-bending stuff. But then the part that really got me was the dual hinges in the tRNAs that work in conjunction with this ratchet effect. And without it, the ratchet effect won't work. And you can't get the correct or you have major errors in getting the correct positioning for the tRNA binding site or codon anticodon binding. And it has to be like, it's like angled. And anyway, they were showing these animations of like how the hinges work in the tRNA molecules. And I'm sitting there watching this, like having my mind blown, as you can imagine, of like, wow, this is fantastic. This is amazing. But then I asked this question to the good doctors in the stream a while ago. I mean, I knew this concept, but I hadn't really thought about it until I saw like an animation. They're showing this whole premise that the stop tRNAs go to an entirely different portion. It's not just it's different and it's doing a stop. It binds in a completely different spot as in the rest of them. It doesn't even go in the normal pathway of the rest of the tRNAs. It comes to a completely different portion where it does the actual termination effect and then actually interacts with a protein, not the ribosome itself directly. And I found that extraordinarily fascinating and just kind of that's a paradox, in my opinion, from an engineering standpoint. Like, how do you possibly explain that from an evolutionary perspective?
Yeah, and I learned also that besides the stop codon, in order for the ribosome to know exactly where to start translation, there is another sequence which is the Shine-Dalgarno sequence, and the messenger RNA has also that sequence, and when it starts, then it binds to the anti Shine-Dalgarno sequence at the large subunit of the ribosome, and it's like how some kind of fixing it, and it detects exactly the right position of the messenger RNA where it has to start the translation process. So it's not just a recognition of the stop codon, because there are also some codons in the middle of the message which are the same as the stop codon. So it requires a second way to recognize where actually to start. Otherwise, it could start in the middle of the sequence, which would, of course, then produce a product which would be not functional. But you have different mechanisms in order for the ribosome to know exactly where it has to start its job. And as well, from an engineering standpoint, how to explain that? And the most fascinating thing is that you have no evolution. You have no intelligence if you discard intelligence. You have no evolution. So it's just randomness, which you have to propose as an original mechanism to make all this stuff. So that's utterly irrational.
Agreed. And, while we've been talking, we've been attempting to have high-level intellectual conversation over here, and Sal is over there photoshopping Professor Dave onto the mountain of stupidity. Yeah, but Angela, your point you're making, I agree with you completely. I mean, it's very interesting. I think this we pull that up again, Sal? Because what's other after you fall off the mountain of stupidity? Was it the Valley of Despair?
Okay. All right, a little disclaimer here. This was what I was showing was a comment that James Stewart, obviously took a little exception to Professor Dave, and so James Stewart specifically put this graph here, and he said Dave is right here at the peak amount stupid. High on confidence, doesn't know very much. He's certainly not out here at the expert level. I mean, that was kind of brutal.
Well, all I gotta say is here in the point I made, and you brought up against Sal about Dr. Tour's. I mean, the whole point of like Dr. Tour 150 H index, like for anybody in academia, that's a mic drop moment of who are you, bro? What you got? Back up your claim that I don't know what I'm talking about, right? Because apparently everybody else thinks I do when it comes to chemistry, right? But in the and what do you say? 100,000 citations. 100,000 citations.
100 and First off, I do take offense that Professor Dave, I call him pretend professor. That's, yeah, that can be his internet handle, but he shouldn't. I don't want people thinking he's a real professor.
In fairness to Professor Dave, he did do a whole disclaimer video on the whole professor thing because he taught a class or something when he was in grad school or whatever.
And he has a Bachelor of Arts in chemistry.
He has a bachelor's in biochemistry and a master's in science education, I believe.
Yeah. So,
but from the macro view, and I think you kind of put this in another context in terms of Dr. Tour and wannabe Professor Dave, it's like some student coming up to this in the context of claiming that Dr. Tour does not understand chemistry. This is the equivalent of somebody coming up to a Heisenberg or Einstein or Planck and being like, you guys don't understand quantum physics. You're not in quantum physics. You don't understand general relativity. You don't understand the principle of general relativity. And then looking at him and being like, what are you talking about? You're claiming that I don't understand my own equations? I wrote the equations. What do you mean I don't understand them? That's the kind of equivalency we're talking about here in terms of you don't understand chemistry. And actually, because chemistry is much more defined than quantum mechanics, for example, and much more known, it's taking it to an even further stretch of you don't understand the basics of Newtonian mechanics, for example, and we don't understand those formulas. And the one that really always gets me is him going on about how biochemistry is somehow different than synthetic chemistry, and he has no standing to be able to explain it. And I'm like, okay, let's think about this. Dr. Tour, synthetic organic chemist. What does that mean by default when you are an organic chemist? That means you have studied how things form in relation to carbon, correct? Carbon is, then inorganic is everything else, right? Well, literally, we're carbon-based life forms, right? And actually looked this up because I had this whole argument with Snake was right months ago. And literally on the Chemistry Association of America website, they talk about how biochemistry is an offshoot of organic chemistry. So if the pinnacle organization of the United States says that it's an offshoot and a subset of organic chemistry, it's its own discipline, but it's also a subset. And if Professor Dave doesn't know this, then he's just continuing to provide evidence for his own lack of understanding and the justification for being placed on Mount Stupid.
I wanted to say, there are some questions in the chat. I'm probably going to miss a few of them. So what's the takeaway? What do you say to skeptics of anything but their presuppositions who say abiogenesis isn't needed for evolution to be true? I would say grant that for the sake of argument, because that still means that, one, evolution doesn't explain abiogenesis, and Richard Dawkins was therefore wrong to say that the problem of design was solved by evolution, because if you're saying abiogenesis is a separate problem, that means evolution doesn't solve it. So if we're able to show that it would still require a miracle, we can still make the design argument there. There are ID proponents who accept universal common ancestry nominally, like Michael Behe's a good example. To some extent, Stephen Meyer's kind of gone back and forth. But come to the origin of life, like Sygart, Michael Behe, probably someone not so well known as Mike Jean, they said that this is evidence. They view it as strong evidence of an intelligent design of some sort. If I'm misrepresenting some of these gentlemen, apologies in advance. But I think so. Let's just grant, for the sake of argument, that evolution doesn't depend on abiogenesis. I'm not saying yes or no. I'm just saying for the sake of argument, it's still a problem. It's still a problem. And evolution, therefore, if they're going to make that argument, that means therefore evolution doesn't solve that problem. And so when Richard Dawkins said Darwin made it possible to be an intellectually fulfilled atheist, that's false right there, just by definition. Because if you're saying evolution doesn't solve abiogenesis, it's like, well, then you can't say Darwin made it possible to be an intellectually fulfilled atheist, because the problem of design is very severe in the first cellular life. And I wanted to say the problem isn't making a replicator. The abiogenesis proponents try to frame it like Dak did, in terms of making a replicator and saying, oh, there's so many different ways to make life. The problem is making a replicator that has the kinds of molecules that are highly improbable, like what we see in life. One example, my favorite, since it touches on casino math so nicely, and the problem with the law and violations of the law of large numbers, is DNA itself. DNA cannot be synthesized. Everything we know about chemistry says that, and this is actually worth a show on, going over a part of Change Tan and Rob Stadler's book on the homolinkage problem in DNA. It's unnatural that all these nucleotides would form and make this nice kind of railway structure. So the problem isn't so much making a replicator, it's making replicators that have, it's making life, or these replicators that have molecules like DNA. We're not even talking about the information structure in DNA to have useful recipes and information. It's just making DNA that has this chemical characteristics. It's a violation of the law of large numbers. It'd be like rolling dice 100 times or 1,000,000 times and expecting them to be all, rolling your dice and getting sevens. It's just ridiculous. And it's a very easy probability argument, one that's very easy to demonstrate in terms of chemistry, but nothing that any of these abiogenesis papers address. And Change Tam is very sharp to point out that when Craig Ventnor tried to synthesize his cell, they had to go to a chemist. So he had all these nucleotides kind of in computer memory. They weren't yet made into DNA. They had to go through a very difficult process. And Dr. Hayes alluded to it. You have these step reactions where you add a reactant in steps. And in fact, in the process of making synthetic DNA, you have to add a reactant, then remove it, stop the reaction, then put the next reactant. So as you're building one base at a time to get it in the nice orientation, you have to build it piecemeal. Otherwise, we're not even talking about a functional DNA in terms of having usable genetic information. It's just making a DNA strand. And they could only get 100 nucleotides strung together with this method. And then they have to take all these fragments and then stitch them together to make 500,000 base genome for their supposed synthetic life. So I don't know where I was. That was a long answer to what's the takeaway, his question.
Yeah, he said thank you already, but I would like to add to that, Sal, that the polymerization is just a subsequent problem to actually make the RNAs or the DNAs in the first place. And you don't require a few, you require thousands or 10,000s or 100,000s, and they have to be all made the same. And you have an infinite possibility to stick them together, to bond them together. And you have an infinite number of possibilities to make the bases. So I would say that one of the biggest abiogenesis problems is the issue of the lack of a mechanism to select actually the ones, the building blocks which are required for life, because you have any kind of possibilities and you have to restrain them to the ones, to the building blocks which are used. And there was no mechanism to make that, to restrain these possibilities. And I think this is a true abiogenesis killer.
Yes. So I want to point the readers to an excellent book that has been forgotten. It's actually a creationist book it's the only creationist book I know from way back that got endorsed by a Nobel Prize winner. And I'm going to show some parts of it. I'm linking it. I'm providing the link to the book because this relates to something. Again, people that know me. I tend to be a little nitpicky, and it's just because I'm concerned about protecting students that are actually matriculating through school, and so this is a way to address kind of the entropy argument, the second law of thermodynamics that was in Dr. Tour's discussion with Brian Miller last night, ever so briefly, like maybe less than 1 minute, literally. But it's also a way to introduce a book that was endorsed by Eugene Wigner, who won the Nobel Prize in physics in the 1960s. And Wigner was one of the early critics of Darwin. He was saying it's hard to believe that the way that our minds work could have been through the process of natural selection as Darwin envisioned, which was kind of a startling statement. And Wigner endorsed this book, and I'll show you the title of the book. It is actually this is the appendix. I hope I can. Let me save this just in case I blow this up, because I want to get the entire title of the book. Let's see if I can get it. The title of the book is Origins and Destiny. And I don't know if I can see if I can. Let me just try to do this. Here it is. Origins and Destiny. Robert Gaines was a physicist at RCA, and he examines God's handiwork. I mean, this was an old book, 1986. And there was an endorsement here by Nobel Prize winner Eugene Wigner. And I don't know where oh, here it is. A careful appeal to the Genesis record and the latest findings of science. And this is Eugene Wigner. He said, I was particularly pleased with Dr. Gaines's refusal of the idea of materialism and the convincing arguments supporting that refusal. In fact, the book will be a welcome response to materialism. Good luck for a good book. And I believe they probably met each other because of their academic affiliations. So this was a very good book. I just wanted to at least plug one of these forgotten books. I think I'm going to try to download it because I'm worried it's going to be lost in the archives. And it's free. You can get it for free. I think that was part of Dr. Gaines's will that he would make this publicly available. But now the part I wanted to cover is in Appendix 2. Just to set the record straight, in Appendix 2, and hopefully this will settle a few things. I'll just read here. The application of information theory to classical statistical mechanics unified the older thermodynamics into quantum statistical mechanics and paved the way to our modern understanding of entropy. We noted earlier that entropy can be correlated but not identified with disorder. So again, I'm trying to encourage people. Welcome, Gene. I'm trying to encourage people not to say entropy is a measure of disorder. That's kind of archaic. And anyone who wants to pursue that, we could talk about that a little later. Entropy can be correlated but not identified with disorder. And we said, moreover, that this correlation is valid. And let me show the, I'm sorry, I totally forgot to share my screen. We noted earlier that entropy can be correlated but not identified with disorder. And we said, moreover, that this correlation is valid in only 3 cases: ideal gases, isotope mixtures, and crystals near 0 degrees Kelvin. The truth of the matter is illustrated by considering the 2 chemically inert gases, helium and argon. In our mind's eye, we imagine 2 balloons, one filled with helium and the other with argon. First, we lower the temperature of both balloons to 0 degrees Kelvin. This makes all the gas molecules stop moving in either balloon. Next, we get the molecules moving by heating both balloons to 300 degrees Kelvin, roughly room temperature. Were we to mathematically calculate the increase in entropy, we would find that it was 20% higher in the argon balloon than in the helium balloon, 154 versus 120 joules per mole per degree Kelvin. But since helium molecules are 10 times lighter than argon molecules, they are moving 3 times faster and thus are more disordered. Here, then, is an example where higher entropy is accompanied by lower disorder, therefore, thereby demonstrating that we cannot identify one with the other. In the particular example cited, the greater argon entropy comes from the closer quantum translational energy levels identified with its greater molecular mass, as described by the Sacker-Tetrode equation. And yes, I studied the Sacker-Tetrode equation. It was miserable. So, I'm just wanted to cross some T's and dot some I's, but I encourage people to see, to look at this free book. And it's one of the older books. It was 1986, and it, as I said, it got an endorsement from Eugene Wigner, that beautiful endorsement right there. So that's what I wanted to share. So Gene, welcome to the panel. Feel free to introduce yourself. I think we may have met before.
Just for a few seconds, I came like two weeks ago. Yep. So I'm Jean from France. So
Jean.
Happy to be here. I've been following your works for like few months, and so that's it.
Oh, were you the one that asked about animals and humans being more evolved, or are you that same Jean?
Yep, that's me. It's Jean Cuivre. So I asked about, yes, it was some chimp-human related question about the post-transcriptions and how it is different from one family to the other.
Well, actually, since you're here, because I really wanted to do a show specifically for you, because you raised that question. So unless there are any objections, I'll try to take it. So, and this is a theme I've wanted to share. So we're kind of wandering off topic from the Ryan Hayes and James Carter and also James Tour, but I guess that's an open mic for you. I raised the issue. So we have all these, the evolutionary biologists will say, well, what does common design explain? Why is there common design? And I've argued there's a stairway. I call it a stairways to understanding. It is, life is constructed, it's optimized for scientific discoverability. One of the things that evolutionary biologists will insist is like, we're not more evolved than other creatures. And I'm just like, well, there are problems with that because humans are far more complex than a bacteria, far more. And the way we could argue it in terms of biochemistry and cell biology is also very interesting. And one of the ways we could do that is by studying post-translational modifications. Otangelo, are you familiar with post-translational modifications?
Well, I know that when the protein comes out of the ribosome, it's shuttled to the endoplasmic reticulum, and there it's further processed. Eventually, it is glycosylated, and then eventually it is tagged and sent to the cell membrane to a specific destination where it will be incorporated in the membrane and then start its operation. That, of course, is everything happening after that it is synthesized, and it's a very complex process, and it requires a lot of data.
Right. And a quick interjection on that too. I think something else that people really need to contemplate if they do understand the basics of protein synthesis. is the untranslated regions of the mRNA actually oftentimes they don't necessarily turn into amino acids, but they serve as different tags and different additional instructions for post-translational modifications that Sal's referring to that are happening in these different locations. And those kinds of components, in my opinion, completely annihilate the concept of these things forming by chance. If you have to have different things in a specific spot that have no chemical, they're not causing a initial reaction until you're in a completely different physical location and you've left the ribosome. It's a whole other dynamic that has to be addressed. Sorry for my tangent there, Sal. I yield.
Oh no, what I'm doing right here is I'm actually looking for a diagram to kind of explain post-translational modification. I think I may have found one here for our viewers. And I'm going to share the screen. And then this will relate to how come I will argue humans are, I know where this came from. I was saying humans are special. You can actually see it biochemically and in terms of the way at the biochemical level. And I'm going to try to demonstrate that. Humans are very, very special. And I think the way that came up is Emery and I were talking about that paper, What's Wrong with Evolutionary Biology? And he was relating a story to how he said we're a little bit different than chimps, and someone in his one of his fellow graduate students got really angry. And I'm just like, well, we can demonstrate it biochemically that we're more evolved than not just chimps, but also other creatures. There is a stairway, and guess who's at the top? Or, you know, at least in some aspects, not all. So I'm going to share this screen here, and this is a what a post-translational modification is. So imagine that you see this beads on a string. These are the amino acids on a protein. And these various amino acids can have different kinds of post-translational modifications. A very common one is if we have a serine amino acid, it can get a phosphate added to it. And that will happen also to threonines and tyrosines. And lysines can be acetylated. Prolines can get hydroxylation of when you can get sulfurs connecting cysteines, creating a sulfur bridge, or what they call a disulfide linkage. Arginines can get methylations and glue. I'm embarrassed. What a glue is. Is it glutamine or glutamic acid? Oh boy, Dr. Carter's going to pounce all over me. I should know this. It can get glutamate. It can get a carboxyl acid group added to it. But there are even more of these. There's glycosylation, as Otangelo referred to. In fact, let me see if I could show this, because humans have lots of these. Heparan sulfate. Let me see if I can get this. There should be some nice pictures of heparin. I had one in one of my biochemistry books, and it was an even better picture. But apologies to the audience.
Dr. Carter saying glutamic acid.
Glutamic acid, yes, and then it can be a glutamate. Glutamic acid can be a glutamate, if I got that right. So thank you, Dr. Carter. So let me see here. We can have this protein here, and then it can have these long carbohydrates attached to it, and these carbohydrates can actually form a code, and it's a complex code. It's not a trivial code, and so some people will hear the sugar code, but that's I'm getting a little bit far from where I was really wanting to talk, because I studied these Topai Summaries. This is actually in a publication, and all I did was I tallied. There's this website where we can go through and see all of the all of the known post-translational modifications. So we have this human topoisomerase 2 alpha, and then we have a paralog human topoisomerase 2b. We actually need both to survive. Now, yeast don't have copies of it, but we were just doing an alignment here, and this was in a publication at the Conference on Experimental Biology, April 2019. So I'm just going to show all the little kind of bits being flipped in critical positions on the topoisomerase as we go from the N-terminus here, and this is the spelling of the topoisomerase, like 100 amino acids or so, and I'm just going to go through it. You're going to see all the possible kinds of post-translational modifications. So we have phosphorylations here, ubiquitinations, cross-linking. And by the way, they're different modifications. There's one set of modifications on the A form versus the B form. And I showed this, by the way, to Dr. Sanford. His jaw dropped. He said, I didn't realize proteins had all this. This is like a computer memory. Every topoisomerase is like a computer memory. I said, in a eukaryote, a lot of the proteins are basically like floating memory chips. And so you could flip these. And these are, I've identified the various portions. But then there's another portion that is really, once you start to get toward the C, what we call the C terminus, toward the, what I call the right hand, or proper terms, the carboxy terminus, the topoisomerase, you get to see far more of these post-translational modifications. And so where is this headed when I'm saying humans are very, very special? One thing you can do is you could take either the human topoisomerase A or topoisomerase B and put it in a yeast. The yeast will live. It doesn't seem to care which it is. You can't do the reverse. We don't have direct experiments because we don't want to play with human lives. We have tested the idea with mice. If you knock out the one of the topoisomerases in a mouse, it'll kill itself. It needs both. That implies that even when we have the same protein across species, the version in the human is a lot more complicated. And then I'm going to do this just for Gene since he's here. He was asking me specifically what paper do we have for that. And when I made that claim, I said, the way to do it is you go to this website called Uniprot, uniprot.org. And you could dial in, like, say, this website's slow, so apologies to the viewers. It's still loading. It's still loading. I'm sorry, Jean.
Yep.
I can't speak French. Did you have any questions while this poor website's still loading?
Yes, about the sequence you showed previously with all the colors. So it means that I want to be sure to understand it. So is the nucleotide sequence exactly the same between all those species, or is it what does the arrows represent?
Okay, thank you for asking, because I know I may be confusing some people. So this is the spelling of the amino acids, which have a corresponding nucleotide. So that we're not actually looking at the gene, we're looking at the expressed protein, the sequence, in terms of the 20 amino acids. So this is the spelling of the amino acid of the same protein, of the protein in the humans here on this row. And let me see if I could just make it a little bit. And then the next row is the chimp, and you could see that it's identical in most spots. There will be variation. So if I probably go to another slide, you'll see a variation. But then we have the mouse here, It's very similar. There are a few differences. And then we go farther and farther away in terms of a different species. And in some cases, there are all these, there can be these gaps here where one species may have more than other species. And then you could see the yeast is spelled very differently than the human up here. Does that sort of make, I'll explain what the arrows are
Okay.
later. So this is a multiple, what they call a multiple sequence alignment. And this is where I say, I don't want creationists to say, oh, we're very different from the chimp. I'm just like, well, I look at diagrams like this a lot, and you could actually see our similarity. It's striking. And there's a reason for that. There's a reason God made it that way.
Yeah, because what I'm looking for is, since you have the scenario of lineage split 6 million years ago, I'm looking for some stuff that could not have pop up in 300,000 generations. And
yeah. Yes, I've been working on that problem. It deals, one of the areas that had been suggested to me, I was sharing this with Dr. Sanford, who did work on the waiting time problem. And I said, look at the zinc finger proteins, and we could look at that. This is, so what I'm doing here right now is actually answering a different question when I was saying, how can I show that humans are very special? So if you could hold that thought, maybe I can address it later.
okay.
Okay. So this, you're asking what the arrows mean. That means that this amino acid can be post-translationally modified. In the post-translational modification again, so like you have a serine, a phosphorus can be, a phosphate group can be added to it. It doesn't have to be added. It can be. That's the important thing. And one thing to point out is whenever you're adding phosphate groups to this protein, you're slightly changing the fold. And so now you can see that if depending on whether it has a phosphate group added or not in all these locations or any of these other post-translational modifications, there's an opportunity to change the fold dynamically. And so I've said, hypothetically, you could have very subtle changes to the fold. We could have hundreds, I mean, like there are like 191 post-translational modifications. Just as a rough order of magnitude, that would be 2 to the 191th power possible different folds. That's huge. So it's not just a static protein that has only one fold. It could have a bazillion different folds because of these post-translational modifications. So I hope that clarifies what it's just a chemical modification. And I need to point out something. There has to be a machine that makes that modification. So how does it find that protein? Well, first that machine has to find the protein, and then it looks for the sequence. There's a sequence here that will identify it as the right location. So like if it's going to do a phosphorylation, this machine called a kinase will somehow find the right protein. It's going to find the right spot in the protein by looking at the sequences to the side, to the left and the right. And then it's going to modify the correct amino acid. And I said, this is a severe problem for evolving, because now these the sequence to the left and the right, you can modify it a little bit, and that kinase still may have a probability of attaching and making the modification, but we change each time we start to change these sequences, we degrade the ability of that post-translational modification to happen. And that may be very, very important. Sometimes a degrading of a single post-translational modification could be devastating. And so this is also an argument that, people say, oh, we've modified the yeast Topai Summaries. It can evolve. It can, lots of random drift. You can't do that to a human. You can't do that. You can't play those games because the human is much more integrated. And this is an illustration of why. So I'll pause here for a moment before I go back to the Uniprot. Jean, can you, if you had questions?
No, that's it. Thanks.
Okay, so let me show. You asked whether there's a peer-reviewed paper. I wish there were. I wish there were. So we can go to the Uniprot webpage, and I happen to know all these proteins have these identifiers, and unless someone tells you in advance what the identifier is, it's really hard to find it. But I happen to know that the topoisomerase 2 alpha, because that's the protein I study, one of them, and I must admit I don't study it as well as my co-author. So you just go to the Uniprot and type something like top2A, and then you could see the one for human, mouse, rat, and somewhere here there's yeast. And I'm just doing this for completeness since you asked if there's a paper. I'm not aware of one, and if it's out there, that'd be great. If there's not, a paper needs to be written. So they just list all these post-translational modifications. Here it is. Amino acid modifications, and this is just a brutally long list here. So when you saw this picture here earlier, what did I do? It took me 6 weeks to do this because I drew this by hand. I went to this listing here on Uniprot. And so like for residue 655, I'd have to go find it somewhere in here and draw, find the right residue. And then I would, let's see if I have it. Yeah, see right here, 655. And I had to draw it there, and it's just miserable because of there are alignment problems. And then like I would be just drawing that in, and you could see all of these here. Now, this is for yeast or bacteria. One, the bacterial homolog of topoisomerase doesn't have any post-translational modifications. It could be that we didn't detect them, but I think that's not the best explanation because we have a lot of machinery in human beings to do all these post-translational modifications. If we do the same for yeast, top 2 yeast, let's see if I could find it. Yep. And then we look for post-translational modifications. This is all we have. We have just a few. So we have 0 for bacteria, a few for yeast, and just oodles, like almost 200 for humans. And that's what I was trying to say. You can show it biochemically that we're special. And there are other ways that we can demonstrate that we're special because of combinatorial gene expression. The polymerases in multicellular creatures are far more complex than they are in bacteria. And this is what they call the G-value paradox. Why is it we have only marginally more genes than a bacteria, yet we're so much more complex? It's in the gene regulation and all these other things. So I just wanted to be complete since you're curious, and I'm really glad for your question.
Yep, and I also heard about orphan genes. So do you know of any, the taxonomy restricted genes? Do you know of anyone that only humans have, and what it does?
I don't know the specific ones. There's a debate on how many. The evolutionists are kind of upset when someone reported that we have 1,000 orphan genes. They said that's not possible. It couldn't go on.
I've seen papers ranging from 900 to 1,400 in humans versus chimps.
Yeah, that's serious. And there are other problems.
I think I found the same numbers, and now I'd like to find a gene that does something and that only belongs to human. could be outstanding to know about it.
Or
Wait,
even doing go on.
I was going to say something else you should think about too, Gene, is not just in the context of humans. You should also look at the growing number of orphan genes just in general, right? The more organism sequences or genomes that are being sequenced, the more they're discovering quote unquote orphan genes. And so, 10 years ago, there was this pretty relatively small number. Fast forward to today, and now it's thousands and thousands and thousands and thousands of them. And there's now we hear all this stuff about, oh, we're so similar. Well, it turns out the total number of orphan genes, from when you look at all the different species, is dramatically greater than the ones that we share. And that premise gets completely glossed over and almost ignored outright by the evolution camp. Because, I mean, honestly, how do you explain that one? If you're going to argue that similarity is the foundational proof, and there's actually now a greater total number of unique ones versus similar, that causes a major problem in all of your logic.
Yeah, what I've tried to say is, I think, I come from I used to be an old Earth creationist. I'm a young Earth creationist now. I think the best argument that we don't share a common ancestor with chimps is if the fossil record, definitely if the Earth is less than 10,000 years old, there's no way we could have evolved from chimpanzees. We're here, our similarities are owing to common design. To me, that's the slam dunk argument. I understand that some people would like to also make the argument and say, okay, let's assume for the sake of argument long ages. Can we still make an argument against common ancestry? It's like, yeah, you can. It's going to be harder. So that's just kind of where, just so you know where I stand on that. I say let's take on the age of the Earth or age of the fossil record argument, because that'll settle everything. Because otherwise we get into these really difficult technical problems in looking at orphan genes and then the waiting time problem. I'm not saying that they're wrong, but this is tough territory. So I expect there are probably people that can talk about orphan genes and the waiting time problem probably more competently than I can. But since we talked, I'm going to try to answer Jean's question. Is there a waiting time problem? And let me see if I could. Is there a problem for evolving certain proteins? And I'll say yes, and it's subtle. So I'm going to show one protein here, and it is the zinc finger protein. This is a human zinc finger protein right here. That's the spelling of it. Let me see if I can make this a little larger. Hopefully you can see that better now. And so this is the amino acid sequence. It's probably around 500 amino acids. There's a pattern here. You could see it right there. There's a non-random pattern in the zinc finger protein, and I'll explain what the zinc finger, why it's called that. And if we use this Venn diagram to also further classify and group the amino acids, we can even colorize this even more. You could see even more non-random patterns here. So let's see. So now let me show what the zinc finger is. Each of these, every line here is a separate zinc finger domain. And what that means, it has a particular grammatical spelling. It's like a syntax, or like a computer syntax. It has to be spelled with certain elements, like the C's have to be in the right position and the H's. But then there's some variability in between. And this is very much like keys or locks, you could tell that these are keys, but they're actually slightly different from each other because they have a different function. And so this each of these domains here connects to a zinc ion. It gives it a very special fold, and it enables. So just some details here. Let me just put this on its side so you can see it creates these special folds here: the zinc finger fold, domain fold. And I'm just showing some things of how this is connected. You could see that each zinc finger will have this architecture. And this relates to the difficulty of evolving things. And what a zinc finger does is one of the roles of a zinc finger, it can target a specific DNA. So we have a lot of proteins that need to find, our genome is like, 3.3 gigabases of DNA. How is it that we can find an individual gene and regulate it in all that? It's huge. Well, the zinc finger is like a lock and key. It'll bounce around and it'll find the right piece of DNA, connect molecular machines to it. That's its role. There are other kinds of zinc fingers. And what I was saying is, this is like trying to evolve a lock and a key to match, because the evolutionists will say, oh, all you have to do is you just have a random walk and it's no problem. You can evolve it. And they build these ridiculous phylogenetic diagrams. I said, guys, this isn't going to work. This is like having a random walk for a key and it needs to match a certain lock. It's going to fail. You're going to have a massive waiting time problem where you're altering the keys and the locks randomly, and then they have to match. How are you going to get a functional system at that point? And when I showed this to the author of one of the papers on waiting time, Dr. Sanford, he said, this is something to file away because this is going to create tremendous waiting time problems. I'm just like, yeah, it's going to be very difficult. So let me see if I have some other. I mean, there are other zinc finger arrays that are just gigantic. But the point is, let's see if I could find something. I don't know if I have it in this. Oh, okay. Here's a picture. Okay, so you have this zinc finger protein. I want to show how it connects. So you have this zinc finger protein here, and it has to connect to the right piece of DNA. But then the other parts of the zinc finger, you have like this sequence up here that enables it to connect to other parts, other molecular machines. And so you have these gigantic complexes here that have to be located on the right spot. And it's going to connect to all these other proteins that are molecular, and you end up creating this molecular machine. This is modifying the chromatin. It's flipping bits on and off. And I'm like, okay, you're not going to be able to, this is very problematic because, by the way, this zinc finger attaches to transposable elements and retroviruses to locate it in the right spot. And just like you're not going to be able to modify the DNA randomly, and you can't modify the zinc finger randomly. This is starting to show the difficulty of evolving a protein. And so this gets into the waiting time problem. How can we evolve either mammals in general, or like, say, primate ancestors into a human? You have to coordinate all of these locks and keys together, and it can't be done randomly. And so if we explore the amount of time it takes for the lock to find the key, so to speak, where you're doing it by random mutation, it is a geological time absurdity, or maybe even astronomical. It'd be older than the age of the universe. So that's my answer. It's like, well, the easy way is to say, okay, if we can prove Noah's flood, we don't have to do all this difficulty. But the nice thing about seeing this is you could see the complexity of the cell. And I've been trying to say, this is the easier way to see the complexity of proteins. Creationists have been citing Doug Ack's work, which is very fine. But when you can actually see the geometric connections, you can actually visualize the difficulty of having interconnecting parts. Oh, you're muted, Otangelo?
I'm sorry. And the same problem goes with the codon-anticodon match in the ribosome. If you have the codon sequence, but you do not have the matching tRNAs with the anticodon, which matches to the mRNA, so nothing goes. So you have both of them. And how can both evolve or merge together? They have to come together. And that's, of course, a big problem. And I guess the lock and key problem goes to all the proteins which have allosteric binding parts where the substrate has to bind to the protein in order to be processed. So I think that goes all along in biology, that problem, and I think it has not been sufficiently acknowledged.
Yes. Jean, did you have any comments?
No. Yes. I have one. Yes, it's interesting because in this, I think it's Michael Behe in some of his works. He talks about the resistance to malaria, I think, and he says that there are two mutations that are codependent and that must occur for a given population of mosquito to become resistant to a given to become resistant to a treatment or something like this. And yes, this is I think and there is this article of Sanford that bounces on Behe's saying that it takes too much time for a mammal population to get two codependent mutations happening, because mosquitoes are by the billions, but humans are not, and also they have this scenario of 10,000 people in Africa, so the odds are very, very low.
Yes, and we're only talking to, I'm going to show you some diagrams to even picture protein and probabilities. This is the public portion of a paper I'm working on, and the reason I made it public was so I could get some feedback. The evolutionary biologists haven't even touched it. I mean, it's like, okay, usually they're very quick to criticize if I make a mistake, and I thank them for their editorial corrections, but they haven't. I posted this publicly to see if it's a good argument, and when they're silent, it's that tells me I think it's a good argument. So let me show visually something about protein probabilities. This is just a toy diagram here. Just totally, this is just a toy diagram, but it gets the point across of how things have to be well fit to connect together in certain contexts, that it can't be random. We can't say that these pieces were formed by random chance, because you clearly see how pieces fit together. And from Bruce Albert's book, Essential Cell Biology, this is a diagram that shows it at the protein level. So each of these here is a protein, or we call it a polypeptide. So I'll just read the caption. A large molecule, such as a protein, can bind to another protein through non-covalent interactions on the surface of each molecule. So some of those interactions can be in terms of the electrical charges that are presented, electrostatic charges. In the aqueous environment of the cell, many individual weak interactions could cause the two proteins to recognize each other specifically and form a tight complex. Shown here is a set of electrostatic attractions between complementary positive and negative charges. So what's the chances that you could make a complex like two complexes that they'll fit together so nicely where you could see the positive and the negative charges align? It has to be also the right strength, and that's a little bit more intricate. A good example of this is the helicase. This is actually 6 copies of the same protein, but to form a working complex, you have to have 6 copies, and then they connect together. And I'll have some diagrams that will show just how many connections there have to be on some of these proteins. So this symmetry that we see here in biology, we also see it here in like the man-made world. I'll show another protein. We talked about topoisomerase alpha. I keep mentioning it because a lot of researchers can't spend too much time studying other proteins. It takes so much study just to understand even one protein. So that's why I talk about topoisomerase a lot. It just happens to be the one that I study. And this is a topoisomerase complex. You can see it's you need two identical copies. It's somewhat like a scissor. In fact, a researcher recently told me, yeah, topoisomerase is like a pair of scissors. It's actually more sophisticated, far more sophisticated than that. And so these two copies connect together. Now I have I'll give you a diagram of just how many connections there are, because from an X-ray crystallography experiment. But there are other ones here. This is a potassium ion channel. And there are actually 4 copies. The individual different colors are the separate proteins, and 4 identical copies make this potassium channel. You could see kind of almost the square shape right here. Very reminds me of a square nut, you know, where it's square here and then there's a hole in the middle. It's kind of like that there. So all this to emphasize all these interconnections. Now, if this looks like, yeah, do we have any proteins that look like that? I'll show you one, the EZH2 complex. And maybe just to show kind of the analogy here. Okay, so we have all these regions here in the EZH2 protein. And you can see the coloring here and how they all have to connect just right to get the fold. And you can see how everything nicely fits together. That is a way to visualize the improbability of this forming in a coherent way. And so this EZH2 complex is part of an even larger complex called the polycomb repression complex. This dark wire here, that's the DNA, and this molecular machine docks to it. That enables, it's going to modify, it's going to do post-translational modifications on the histone proteins. That changes the quality of your skin, makes it different between the skin on your eyelids versus the skin on the soles of your feet. There is some complex stuff here, and these proteins have to be shaped. So this is giving a feel for the improbability of making these. So what I often say is these evolutionists will point to these trivial changes and say, oh, look, it's so easy to make new function. And I say, yeah, it's easy for a tornado to pass through a junkyard and make paperweights, you know, just these little things you can put on paper so that the wind doesn't blow them away. Just trivial function. But you can't have a tornado pass through a junkyard and make an airplane, a 747 jetliner. So now I'm going to show that I talked about the topoisomerase. Let me see if I could find it here. Yeah. So we have this topoisomerase here. What I did, and let me try to make this a little bigger. So this is these letters here are the amino acids spelling out one of the topoisomerase polypeptides. So to make a topoisomerase complex, you need to take this recipe here and spell it out twice. All of the colored points here, like the purple and the green and the yellow, are the connection points. Now, yeah, I don't know how many we can knock out, but it's going to fail if you knock out enough of them. Question?
This is the question I had. In the DNA, there are 2 copies of the same sequence, or is it the same sequence being transcribed twice to make the protein?
Very good question. DNA has the one strand and then a complementary strand. This is a different situation where the transcription has to happen twice, literally twice, and then make 2 copies. So for some proteins, you only need to go 1 pass. For some proteins like topoisomerase, it's 2 passes just to make enough. And then you have proteins like the Helicase. It has to make 6 passes and make 6 copies just to make one single helicase. And so these are really great questions. So what I was trying to show is when we can actually quantify, in some cases how precise the number of connection points. So I counted 54 connection points here. And to relate it to an earlier diagram, where did I have it? Bruce Alberts. So Bruce Alberts was showing, you see all the connection points here in this diagram. So first off, it has to be physically folded so that it presents it in the right place. But then we can also count how many connections there are in the amino acid spelling, which I tried to do here. There are 54 connections. And there are all sorts of ways we can also see the layers of organization. There are layers of organization of the different parts of the topoisomerase. You should, I encourage the viewers to look at the topoisomerase videos to see what they do. It is mind-boggling.
And is it topoisomerase 1, 2, 3, 4? Because I think there are lots of topoisomerase.
Yes, there is a family, and I only focused on the topoisomerase 2.
Okay.
And I'm embarrassed to say I don't understand any of the other ones because I haven't studied them, and I focus mostly on the topoisomerase alpha. There's a 2 alpha. The topoisomerase 2 beta could actually be more interesting, and because it does a lot of things in humans that it doesn't do in yeast, and we're beginning to learn that. So if there are questions in the chat, I'm going to look for them. Stuff I watch sometimes. He said sense and antisense. I think that's correct regarding DNA. You can say the sense and the antisense strand. And James Carter, do you happen to know the average number of amino acids for an alpha helix versus a beta? Actually, it's alpha helix versus beta strand or beta sheet. I showed earlier the zinc finger proteins. The alpha helices could be as small as 4 amino acids. And they define I think one way that they can define whether it's an alpha helix versus a beta strand is the configuration of the hydrogen bonds between the amino acids. So, and the beta strands are actually kind of short. Logical. Why don't I show you a picture? I happen to have a picture that can actually show you the beta strands. So you could see the relative sizes there. So the alpha helix is in yellow. So these are alpha helices. The red are the turns. The greens are the beta strands. So maybe that will show you visually just to get a feel for how long some of these are. So you can see they're variable length. We have some alpha helices that are extremely long, and then some that are short. There are only 4. And some of the beta strands we have here are, you can see kind of the length there.
You're not sharing your screen right now.
Oh, apologies. I keep forgetting. Here you go. There you go. I want to acknowledge Dr. Cardinal. He's an evolutionary biologist. He said, I apologize for, I've been in and out, so I apologize if I missed it, but regarding waiting time problem, did anyone bring up the parallel nature of evolution and its relevance? I brought up the problem of waiting time when a zinc finger protein has to co-evolve with like say a transposon that it binds to. I think the whole thing about coevolution is not statistically sound to say it can just happen, and also within reasonable limits. It's a question that should be explored. So let me just put it there. But I'm trying to address Logical Probable's question about the length of beta sheets or beta strands and alpha helices, and I'm just trying to show a visualization in the Topai Summaries. One can see the different lengths. The yellow are alpha helices, so we could see like this alpha helice up here. Hopefully you could see my mouse. This alpha helice here is only 4 amino acids, and then we have some that are much longer than that. And then we also have beta strands, and you could see that in the green color. Now, for those wondering how I got this, it's again that Uniprot website, which I showed earlier. And yes, I painfully went through that Uniprot, and they're giving the coordinates, and I colorized it. That took like a day. So this is a day of work to colorize the alpha helices and beta strands here. And you can see the level of organization. So I'm just going to show the levels of organization. We have the organization in terms of the alpha helices and beta strands, and then these things called turns. And perhaps I think I can show this visually on the Topai Summaries. Let me see. Yep, there's Topai Summaries. So protein scientists like to use these things called Richardson ribbon diagrams. And anytime you see this like thing that looks like a ribbon, that's an alpha helice. And then these things with the arrows here, those are beta strands. So then when I went to the, that's collagen, sorry. Oops, that's not what I wanted to show. Apologies to the readers. I'm going to have to just go through this so I could find what I was looking for. Yep. So if I have, maybe I know what I could do. Let me cheat a little bit here. I'm going to copy this up into so when you see these alpha helices here, sorry, this is obnoxious. It'll correspond to one of these little ribbons here. I don't know. I would bet some of these longer ones here would correspond to these long alpha helices here. And then some of these green things would be the beta strands up here. I believe, well, I'm going to hurt myself here if I try to identify what's the C and the N terminus. But anyway, that's one level of organization in terms of this beta strands and alpha helices. But then there's another level of organization where we identify the actual pieces and their functional significance. I should point out this section here that says DQ. This one here, that was the subject of a PhD dissertation, the DQ, to try to identify its function. And so there are all these different parts here that I colorized. And yes, that was another half day of work to colorize it, to dig up. This is an interesting piece here, this nuclear export signal, and then this nuclear localization signal. These are like postal codes that tell where to locate the topoisomerase in the cell. So in some modes, it'll say go out to the cytoplasm. In another side, in another mode, it'll say go inside the nucleus. And so these are specific postal codes here. And so you could see that even though this is only like 1,500 amino acids. Oh, sorry. This is only 1,500 amino acids. The difficulty in understanding all the functions, it is really just a lot of functionality and information just packed into here. And then on top of that, these are the post-translational modifications. And like I said, I've argued that humans are very special because we have way more of these basically these colored things. You won't find it that many in yeast, and to my knowledge, we don't find any in the bacterial homolog. Therefore, it is fair to say, even though evolutionary biologists may cringe at me saying this, we're far more evolved. If we're going to assume common ancestry, we evolved a lot more because it takes a lot more evolution to construct this level of complexity. And it's not just the Topai Summaries. We could see it almost every level. And see if I have another diagram. Oh, yeah. So the way that I can represent these post-translational modifications, I can represent it like that, which is prettier, but it's really the same. It's the same. Let's see if I could find it. Did I lose that diagram? Yeah. This is basically showing the same information more compactly than this kind of fancy representation here. And so those are at least the minimum level. So in addition to post-translational modifications, we have these are called interface points. These are all the connection points. So that we call this a Topai Summaries dimer, di meaning two. So it takes two pieces to come together. And I counted 54 connection points. And this again is trying to show the idea that Bruce Albert stated in his Essential Cell Biology actually understates the number of connection points if we deal with some of these specific proteins like Topai Summaries. Questions? I did mean to, you can unmute yourself, guys, and I think Atangelo dropped out. Let me, if anyone would like to join in the show, I'm going to open. We just have to be well behaved, please, for the sake of the kids, and I'm not kidding. I'm going to try to put the invitation. I'm going to repost it here. Any questions?
No, but it's very enlightening because you first have to get the right sequence. Then you have to get a mutation that tells the machinery to read twice the same sequence, and then you have to have those two sequences stick one with another. So it's very fun to to try to imagine how it could arise by accumulation of mutations.
Yes, and so the complexes that some of them that I try to share is like this one. This is like one of my favorite ones here. This is one of them right here. That's one of my favorite right there. And I had another favorite. Oh wait, wrong slide. Let's see. That one. That's the polycomb repression complex 2. That's just, look at all the connections that have to happen. So this diagram understates the difficulty of enabling this one to connect properly to this one, because even this one has to fold and connect to itself. And I showed earlier. So this piece here called EZH1/2, the EZH2 version is like this. So
Yep.
Yes, try to randomly mutate it so that it folds well to itself. So then, it can also connect and anticipate connecting to all these. And so all of these will have what we call those interface points. And I've been trying to collect interface points for all these things. And it's actually it's not easy, but then when you start counting them up, it's like, that's a lot. Because if we don't have things like this, we'll be malformed.
Yeah, I was watching a very fascinating presentation from Howard Chang. I believe he's let's see, he is from Stanford, I believe. I think he's the head of their genetics department. There, he was giving a very interesting lecture series on a variety of things, but really getting into the some of the transcription factors. And he was like showing how there's like 85 in eukaryotes, 85 different components that are necessary for that process. And
Oh, the number's up to 85 now.
yeah, and then they was actually pointing out another little chunk that they didn't know. They knew something was happening there, but they didn't know exactly what it was yet. And so when you really think about all of those different components that are being necessary for the execution, and then one of the other points he was making was the ridiculous amount of protein-protein interaction, and how many of them are released, like they come in, bind, do their little function, are released, new ones come in to like get everything ready, take the next step, they get released, a new set comes in, binds, does their little things to get ready, and then the final factors come in and do the the final catalyst, and then boom, now you have the whole process. And yeah, it's a very in-depth, detailed, step-by-step process that has to happen. But for us to even contemplate it and to consider it and to think about it and diagram it is very intricate. But it's happening in seconds in your body. I mean, to me, that's just amazing when you think about that. Like, we can't even explain it fast enough in terms of like actual comparison to what's going on. And then you have to have all these components have been built separate from that whole process, completely separate from the DNA itself. To me, that's just how do you come up with any explanation for proteins that never chemically interact with the DNA? How do you form that function?
There were some questions in the chat. One reason it's a little hard to be hosting a open mic or a talk is I have to handle all the technical stuff, and I apologize in advance if I miss something. So some questions regarding the alpha helices and the hydrogen bonds. This is a diagram of how an alpha helix forms. And so every time you see an R, that's a different amino acid. And we could see how the one amino acid forms a hydrogen bond with another amino acid. I mean, the geometry of how this works to actually form a hydrogen bond, it's just the way that we have these formed that will define the alpha helix. And it's kind of funny to see then we can have a alpha helix with as few as 4 amino acids. So we might have one that just has 4 amino acids, and that would count as an alpha helix. But there's some that are longer. So I wanted to. Are H bonds any harder to break apart than covalent? They're much easier to break apart. In Bruce Albert's book, Essential Cell Biology, they give actually the amount of energy in terms of electron volts or joules to break apart a covalent bond. Covalent bonds are, I think, the hardest to break apart. Then next would be ionic bonds, which are actually partially covalent bonds. You can look up an ionic bond. They'll say that ionic bond is not. It does have an element of covalence to it. Then there are other bonds. Low on the list would be hydrogen bonds. So hydrogen bonds are very easy to break apart. And there was other questions. One by Creation Myth, who we know as Dr. Dan. He did ask a question, and I feel bad because I want to answer it. And I'm really sorry if Dr. Dan, if I miss it, my apologies. It was something about is there only one way to build a protein? No, I was trying to say that there are multiple ways we can build lock. There are an infinite number of ways we can build locks and keys. It doesn't make it highly probable that a given, just because there are an infinite number of ways to make lock and key pairs doesn't make it highly probable that, I could just grind down a key and it's going to fit a given lock. And that's the problem with, that's the way I'm framing the issue of not even functional proteins, but proteins that can even connect and form a complex. So I was trying to show these illustrations of how I look at the protein probability issue. I don't even go so far as function. I was talking about, let me show my screen here. Even before we talk about function, can we even get the parts to connect to themselves or to each other to form a complex? And that's not so trivial. That's not so trivial. To get them to form, like say in this case, a helicase, can we get the individual parts to form and connect together? And then that's not even addition to being able to do something useful. We'd be dead without a system like this, or a system like Topai Summaries. So that's how I'm approaching the protein probability problem. And then I also covered the zinc finger proteins and their binding. Any comments, gentlemen? Oh, someone's made a submission.
Yeah, Dr. Cardinal has.
Wow. Well, if he has nothing to lose, that's a good wager.
Well, actually, he has nothing to lose. Well, here's the thing: is I actually have zero problem with paying out the winners if they can explain how they did it, how they cracked it, and how the process, or they can put it in the caveats, they would come on a live stream with me, which I'll set up for the next weekend, explain the process of cracking the code, how they determine the alphabet value assignments, and how this process is different than the value assignments for nucleotide base pair codons and amino acids. I'm actually excited to have Dr. Cardinal come on and explain that, because he is categorically denied that code mapping applies to the genetic code.
So could you explain your bet? Maybe this is a chance for some free advertising for your cash prize. If I can even try to, why don't I try to even put it, I'll put a link and you can promote your cash prize in your channel.
So
I'll have to go. See you next time, guys.
Oh, Jean, thank you. Thank you for supporting my channel and all your questions. And I hope we could be of service to you over the coming year. It's most of my audience obviously has been targeted toward biology students, but it would be good to be able to reach out to people who are non-biology students, because they're a very important part of the scientific enterprise. So hopefully over the year I can make some videos that kind of plug some of the holes and to help people that haven't gone through a biology curriculum.
Okay.
Take care, Jean. Thank you for joining us from France. Bravo.
Yep. Merci. Okay, thanks very much. Have a good evening.
You too. Wow. I have people from Nigeria, from Germany, and France. This is great.
Yeah, getting some popularity around the world. Should be good stuff. But yeah, the in the context of the competition side, this is not it shouldn't be rocket science. It's I assigned alphabet values to codons and then created a message. And Anyway, it's the whole purpose of me doing this is to, because it's totally crackable. I mean, it's a 1-to-1 alphabet assignment. It's not that complicated. The reason I'm doing this is I really want to force some EVOs to publicly admit on video that the value assignment of alphabet to alphabet and coding is, I just want to be like, okay, it's codons to alphabet, codons to amino acids. How is that how is that different in any context whatsoever? And when you're getting into things like beta strands, alpha helices, turns, hinges, all these different things that we're looking at that have specified spellings, how is this not the exact same as what you had to, or was created and what you were able to decode? And since I have Dr. Dan Stern-Cardinal claiming specifically that it is not code in email, when I asked, he also refused to delineate it in a email chain. I'm just interested to see him either publicly accept that as the case, or whoever it is, publicly accept that as the case, or deny that as the case. And then since there's papers that actually state this specifically, I'd love to have a PhD at Rutgers University deny and formally denounce their peers. So it should be fun.
I just want to point this out to the people in the chat. A woman in my church is referring 13-year-old girls to this channel. So I just want to alert you guys, we have to try to be civil with each other on this channel. It's rare that I do open mics, but I was just so pumped after hearing Dr. Hayes and Dr. Carter and Dr. Tour last night that I just couldn't help myself. And I said, I'm not going to do live streams and host them, but I broke my own rule because I was so excited and I just wanted to talk. I just had to talk with my friends. And at least so far, my mom hasn't needed any attention, so I've been able to talk. So guys in the chat, please just try to moderate yourself. I know you're very passionate, but I'm just alerting you to the fact I'm trying to keep this channel in particular friendly to independent scholars, but particularly to homeschoolers, both parents and their children. So go on, John. And John, welcome.
No, that's all I have to say. I'm actually going to call it a wrap. I got to get some food, and I'm going to lay down. I'm going to listen to Dr. Tour's stream that's coming up, and I'm going to get some sleep because I did not sleep well last night, as you may imagine.
Yes, for those who joined us late, I'm glad to say John is safe. He had spent 12 hours in his car because he was stuck in ice, and I'm just glad he's okay.
I appreciate it.
Praise God for that. And thank you, even though you're tired, thank you for joining this live stream. We're going on 2 hours, and it's probably even longer than I thought I could manage. So
no, it was fun. It was fun. Yeah, like I said, everybody, don't forget. I suggest you wrap up here pretty soon, so because the next episode of Dr. Tour's bashing of wannabe Professor Dave starts at 7.
Oh,
or 8 your time, I guess.
Oh, I didn't know that. So, hey guys, did you hear that, guys? I didn't know that. So take care, John. I didn't know that there.
Oh, good. Take care, John.
Yeah. Oh my goodness.
Yeah, I just wanted to say hi. If you're closing up, that's okay too.
Oh, thanks. Well, I mean, if Dr. Tour is going to be coming on soon, I don't want to be competing with that. Oh my goodness. Can someone, if they can find the link to Dr. Tour's next talk, they're welcome to post it in the chat. So before I forget, Dr. Dan, I thank you for visiting. I wanted to say thank you for introducing me to the biology OpenStax. I'm using OpenStax chemistry as I'm trying to teach I'm trying to teach myself chemistry, and I'm making videos partly so I could teach myself, relearn what I've mostly forgotten, but I've been going through OpenStax. So George Bond is alerting me, yes, Dr. Tour in 20 minutes. And if someone could post the link to that, we'll be wrapping up this stream. If there are any questions, oh yes, Dr. Dan says textbooks are a scam. That's one thing I think Dr. Dan and I share a passion about, is not seeing students being taken advantage of. And I admire him for looking after his students. And I appreciate his passion for seeing them treated well as they try to matriculate through university. At least when I went to school, it was actually affordable, not like what it is now. And so I'm looking at the chat here. If there are any other, if there aren't any other comments, I'm going to be shutting this down. And I look forward to seeing you all at Dr. Tour's show tonight. So before I close, this was the funny part of Dr. Tour's. In case some of you missed it, I'm going to share this one more time. This was actually kind of on the mean side, but Dr. Tour last night showed this Dunning-Kruger curve, and he said, Professor Dave is right there at the peak of Mount Stupid. I was just like, whoa. So anyway, I just thought I just cracked up laughing. So anyway, guys, thank you all for, thank you, Jungle, for dropping in, and thank you all for joining me at this after show. And a special thanks to Standing for Truth for having that discussion with Dr. Ryan Hayes and Dr. James Carter. So until we meet again, take care and God bless you.